For decades, quantum computing was the stuff of science fiction. Today, it's a race, not for pure speed, but for a whole new kind of power. We're standing at the edge of a technological revolution that could redefine everything, from medicine and material science to finance and artificial intelligence. And at the center of this revolution, the qubit. Building stable, powerful qubits has been a monumental challenge. Errors, instability, decoherence, these are the enemies of quantum computation. For years, tech giants like Google and IBM have been leading the charge, battling these quantum foes. Then came a seismic announcement. Microsoft, after years of quiet research, unveiled Majorana 1. This isn't just another chip. It's a bold move using a radical new type of qubit called the topological qubit. Is this a game changer? Could Majorana 1 put Microsoft in the lead of the quantum race? Perhaps even overtaking Google and IBM? That's what we're decoding today. To truly appreciate Microsoft's announcement, we first need to get our basics straight. Think of a classical computer as using bits, simple zeros and ones. Now imagine a bit as a coin that's either heads or tails. A qubit, on the other hand, is like that coin spinning in midair, heads, tails, and everything in between, all at once. That's called superposition. Then there's entanglement. Imagine two spinning coins that are mysteriously linked. When you check one, you instantly know the state of the other no matter how far apart they are. This interconnectedness is what gives quantum computers their potential power. The promise? To solve problems that even our most powerful supercomputers can't touch. Think drug discovery, advanced materials, cracking modern encryption. The possibilities are huge. But here's the catch. Qubits are incredibly fragile. They're prone to noise and disturbances, which lead to errors. This is what we call decoherence, and it's been the biggest hurdle in building these machines. Let's break down the key players in this quantum race. Google's superconducting qubits. Google has been a frontrunner, pioneering superconducting qubits. Their latest chip, Willow, boasts 105 qubits and has demonstrated computations that, if done classically, would take supercomputers 10 septillion years to complete. Although their 2019 quantum supremacy claim with Sycamore was contested by IBM, Willow represents significant progress in error correction and speed. Their technology is fast and has come a long way, but those qubits are notoriously sensitive to noise, meaning error correction is a real challenge. IBM's practical quantum computing. IBM's pragmatic approach advances modular superconducting systems. Their Quantum System 2, featuring chips with 133 qubits each, aims for scalable, fault-tolerant design by 2033. By focusing on reducing errors and integrating practical applications, IBM's Eagle processor demonstrates their commitment to solving real-world problems over simply breaking records. This deliberate strategy underscores IBM's dedication to building quantum computers that are immediately useful, even if it means taking more time to perfect the technology. Microsoft's Majorana 1 and topological qubits. Now, here's where things get exciting. Microsoft enters the scene with Majorana 1, a chip that bets on a completely different approach using topological qubits. So, what's the big deal about topological qubits? They're built on something called Majorana particles, which are self-conjugate. In simple terms, they're their own antiparticles. This unique property means they can naturally suppress certain types of errors, making them inherently more stable. And here's a fun fact. While Microsoft's chip currently showcases 8 topological qubits, the design is meant to scale up to 1 million qubits on a single chip. Imagine that. A quantum chip as compact as something that could fit in the palm of your hand, yet powerful enough to tackle problems that are currently unsolvable. So, how do these approaches stack up? Google and IBM have been refining their superconducting qubits for years. They're fast and mature, but also inherently fragile, which means you need lots of error correction, a tricky and resource-heavy task. On the other hand, Microsoft's Majorana 1 promises a fundamentally more stable solution. If topological qubits can really deliver on their promise of built-in error protection, scaling up might be a lot simpler. But let's be clear, this technology is still in its early stages. While it's an impressive scientific achievement, turning 8 qubits into a full-scale, fault-tolerant quantum computer is no small feat. There's also a note of healthy skepticism. You might recall that Microsoft had a high-profile retraction of a paper in 2018 related to Majorana fermions. So, while Majorana 1 is promising, it's part of a long journey, and independent validation is still needed. So is Majorana 1 the breakthrough that Microsoft claims it to be? There's no doubt, it's a significant step forward. Demonstrating the potential of topological qubits in a fabricated chip is a major scientific milestone. However, we should keep our feet on the ground. Majorana 1 is still in its infancy. Scaling up production, achieving high qubit counts, and integrating everything into a full-stack quantum computer will take time, years, maybe even decades. Yet, if Microsoft can overcome these engineering challenges, Majorana 1 could indeed be revolutionary. The race for quantum supremacy is far from over. Microsoft's Majorana 1 has injected fresh energy into the competition. Google and IBM aren't sitting still. They're continuously pushing the boundaries of their technologies. So, who will win this quantum race? Will topological qubits prove to be the superior path, or will superconducting qubits win the day? And what real-world impact will these quantum machines have when they finally arrive? One thing's for sure, the quantum revolution is well underway. Microsoft's announcement signals that this race is getting more intense and unpredictable every day. The future of computing is being written, one qubit at a time, and it might just be the most exciting chapter yet. Before we wrap up, I'd love to hear your thoughts. Do you believe Microsoft's topological qubit approach could redefine the future of quantum computing? Drop your comments below and join the conversation. And if there's another topic you're curious about, let us know. We're here to explore it with you. Stay tuned as we continue to decode these groundbreaking developments. Thanks for watching.